Welcome to this talk on our paper MetaKernelGAN kernel for blind super resolution kernel estimation, where I'll be summarizing the key contributions, results, and limitations of this work. Now the main task here is to estimate the degradation operation used to downsample the HR image. In particular, the closer the estimated kernel is to the ground truth, the better the resulting upsampling quality. Now, existing works can be mainly split into two categories: works that employ supervised learning implicitly to learn the degradation representation jointly with a super resolution model on a given dataset. This often results in good performance if the test degradation is similar to the degradation used in the training set. On the other hand, works that employ unsupervised learning typically learns degradation representation for each given image at test time. So this generalizes better to unseen degradation, but this is also often really costly with thousands of training iterations per image in order to derive the degradation. It's also quite unstable as it aims to learn from a single image. Now our goal here is to combine the best of both worlds. So ideally we would want to minimize the limitations of the unsupervised learning approaches by expediting or stabilizing the test time adaptation process. And to achieve that goal, we aim to use supervised learning to learn from the unsupervised learner. So in other words, we aim to meta-train the initialization of the unsupervised downstream model such that the downstream performance is optimized. So in the figure, each dashed line represents an unsupervised learning task, and the bow arrow represents the MetaKernelGAN initialization. Now for our unsupervised learner, we adopt a previous work, kernel-GAN, which uses a GAN-based approach to learn the downsampling degradation process of the given image. So specifically, given the image, kernel-GAN deploys a deep linear generator to obtain the downsampled image, and a discriminator to discriminate between the patch distributions between the given image and its downsampled variant. The kernel can then be represented with the parameters of the deep linear generator. Now one of the main limitations of this work is the generator and the discriminator. They're both trained from scratch for each image. So depending on the image, it might be slow and unstable. So the goal of our approach is to learn a better initial set of parameters, so during inference we don't have to start from scratch and can speed up this adaptation process. Specifically, instead of starting from random initialization for each given image, we meta-learn both the generator and discriminator initial parameters such that the generator starts from a reasonable kernel estimate and the discriminator doesn't fall behind. In other words, this allows us to meta-train across a set of external image information in order to learn a kernel initialization that is able to rapidly adapt using the internal information from each given image. So in the inner loop, we have our unsupervised learning, where we run several tasks of our variant of kernel-GAN, where each task is the internal learning of a given image. So for those of you who are familiar with kernel-GAN, we know that kernel-GAN employs many different regularization terms, along with the need to tune the hyperparameters in order to restrict the number of possible kernel solutions. Now in our case, because the parameters of the generator theta g and the parameters of discriminator theta d, they're not initialized from scratch, right? So we only need to use one regularization term, which is to incentivize the kernel to sum to 1. And we saw that just having one regularization empirically works really well, and this makes our approach much easier to tune. And then in the outer loop, we can use the ground truth kernel to learn across different internal learning tasks, and which we use to update the initial parameters for both the G and D. This results in really fast kernel adaptation during inference. So the image shows the kernel of different tasks from 0 to 25 all the way up to 500 test time adaptation steps, along with the ground truth kernel on the left. Notably, instead of starting from scratch at step 0, our approach starts with kind of like a Gaussian-like kernel So in the case where the image has limited internal information, like a really small image or noisy image, our approach would just fall back on this initial kernel. This also results in a more stable adaptation. So in the figure from left to right, we plot the kernel PSNR, the distance between the estimated kernel covariance with its ground truth kernel, as well as the resulting image PSNR when we use the estimated kernel for upsampling. So our approach, which is represented by the green line, doesn't have much fluctuations as compared to previous works. Now we did quite a comprehensive evaluation with a wide range of previous works. So these are just like standard benchmarks, upsampling factors, and degradations that we use, and we compare with mainly 3 lines of works found in the literature. So the first is the patch recurrent methods like kernel-GAN, which kind of exploits the internal patch distributions of the image itself to explicitly learn the degradation. And then we have joint learning methods, which learns both the kernel and the supervised image jointly. And lastly, we have the supervised implicit estimation method, which avoids explicitly estimating the kernel, but instead learn a degradation representation optimized directly in the image space in a supervised manner. Now all the results are in the paper. Just to summarize, we beat all these previous works in terms of performance and cost and most benchmarks and scenarios. So for example, in this slide, we show one of these examples, and there are many more examples in the paper. This table shows the inference runtime and memory cost of estimating a kernel, which for memory cost, we're kind of similar to kernel-GAN because during inference, we're just doing the internal learning process. But we are taking way less adaptation steps, or way fewer adaptation steps, so naturally we're going to be much faster. This makes our method more deployable as well in real-world situations compared to previous works. Now there are a few ablation studies in the paper, and one of the most interesting ones is comparing our approach against kernel-GAN that is just trained in a supervised manner, which we call dataset kernel-GAN, or DS kernel-GAN. So as seen in this particular example, DS kernel-GAN doesn't have an inner loop, and hence explicitly learn from the adaptation process, so it's more susceptible to adapt to faulty kernels, right? So for example, having non-zero values that are discontinuous, as shown in the slides, right? So DS kernel-GAN is just the outer loop. We're just taking the ground truth kernel and we're just training it on that. So it doesn't have this inner loop where it learns from this adaptation process. So another ablation is where we only meta-train the generator but not the discriminator. So this results in inferior kernel estimation performance, as shown in the purple line in the figure. And this is mainly because the discriminator is trained from scratch for each image, while the generator it starts from quite a decent kernel, right? So it dominates at the start of the adaptation, leading to inadequate generator feedback from the discriminator. So in the paper, we list several limitations and possible further directions. So 2 of these limitations include MetaKernelGAN limited ability to handle images that are extremely noisy or tiny. The second limitation is the optimal number of adaptation steps is still dependent on the given image at test time, but we naturally find that after 200 steps is somewhat reasonable. And that's it. If you have any further questions after reading our paper, feel free to drop me an email. Yeah, thanks for listening.